Okay, thank you for the introduction, and thank you all for coming. Today, I'm going to talk about model-agnostic improvements in NLP. So please let me know if I need to speak louder, because I'm not feeling very well, so my voice might be a bit weak. But can you hear me okay? Okay, so before we get into that, I would like to talk about what I mean by model-agnostic. Okay, so let's say that we have an NLP system or an NLP model, and we want to improve the performance. Okay, so here's a typical NLP pipeline. We usually have text data, so this could be a corpus, right? And then we need to use this text as an input to our machine learning model. Okay, so we usually choose like a function that could take this text data and create like a feature factor usually, which is taken by our model as an input, right? So the feature factor would be like the red box over there. And then we choose our machine learning model, and then we learn the set of parameters associated with the model, so that would be the green box, right? And then somehow like we can also incorporate like our linguistic bias throughout this pipeline. Okay, I would argue that the majority of NLP research, so when we want to get improvements on our tasks, we tend to do it by improved modeling, which means that we introduce better models. So for example, we can move from linear models to nonlinear models, or from convex model to non-convex models. Like maybe we were using SVM, we replace it with latent variable SVMs, or logistic regression to neural network and things like that. Now, there is nothing wrong with this. In fact, sometimes I also do that. But so this kind of improvements is what I would call model specific, because we're changing the model class, right? So we're moving like from one model class to something either more expressive or it has better statistical guarantees, basically. So that's not going to be the focus of our talk today. So today I'm going to talk about how we can try to incorporate linguistic bias to improve our machine learning models in a model-agnostic way. So I would like to be clear from the very beginning that it does not work with any kind of model classes, but it would work at least with more than one model class. So it would work with like several, maybe 3 or 4 or something like that. So we'll see how we can do that. And then in the second part of the talk, I'm going to talk about how we can optimize these representations that we use as an input to our machine learning model to get better performance. So this part is a little bit more general. At least in theory, it works with any kind of model class, but I've only tried it with like several model classes, basically. But in theory, it should work like with any kind of model classes. Okay, so that's the basic idea, and here's an outline of my talk today. So first, I'm going to talk about how we can encode a linguistic bias or linguistic knowledge using a regularization function. So this is based on my work last year at ICML and ACL. And in the second part of the talk, I'm going to talk about how we can optimize text representation. So this is more of an ongoing work. The paper is still under review, but there is a draft on arXiv. It's also related to some of my work last year at AI Stats. Okay. Okay, so throughout this talk, I'm going to use text categorization as the application, but I would like to emphasize that the idea is general enough that it should be applicable to other NLP problems as well. But we're going to use like text categorization because it's simple and everyone knows it to illustrate the idea, basically. Okay, so let's start with encoding linguistic knowledge using regularization. Okay, so what kind of linguistic bias that I'm talking about? So here's an example of a movie review, and let's say that we're interested in predicting whether this is a positive review or a negative review. Okay, I know there are some typos there, but it's actually like from the actual reviews. So if we ask a human, hey, do you think this is a positive review or a negative review? So we have like some linguistic knowledge that makes it easier for us. For example, we know that a piece of text consists of sentences, right? And perhaps like we know that not all sentences are actually telling us what the sentiment of this review is. Only a subset of them are actually relevant, and the others actually introduce more noise than signal, basically. So for example, in this case, this is actually labeled as a positive review, and we can take a look at like the red sentence. For example, I enjoyed it, or the purple sentence, the last sentence, the acting is very good. So these two sentences tell us that this is a positive review, right? Whereas other sentences, well, maybe they tell us it's a positive review, but it's a little bit more ambiguous. Okay, so that's like the kind of structures that we want to encode. It's a very simple one, sentences, right, sentence boundaries. But there's also other more complex structures like syntactic trees or word meanings or phrases. So we can incorporate these more complex structures in a similar way. In fact, I've done that. So this is mostly my ACL paper, but to give an overview of the idea, we're going to use like the simplest one because it's easier to get. So we're going to talk about linguistic structure in the form of sentences for now. But this, I will also talk briefly about like incorporating other more complex structures using regularization. Okay. So that's basically what we did. We introduced a class of regularization functions that exploits the intuition that only some parts of an input are relevant to the prediction task. So in our case, we have text. Text consists of multiple sentences, and we know only a subset of the sentences are relevant to the prediction task, right? But this can also be applied to computer vision. I know some of you guys work on computer vision here. So for example, if we want to label an image, right, and let's say that, oh, I know it's not as easy as detecting sentence boundaries, but let's say we know that an image consists of like multiple entities, and perhaps like not all of these entities are relevant to predicting the label of this image, right? So a similar idea can also be applied in that case, I think. Yes?
So is your hypothesis that not all words are important in prediction, or not all sentences?
Not all sentences, like specific, like in the form of like sentence structures. So like the previous example, right? I mean, not all words, yeah, obviously we already know that, but we want to go like into like more complex structures, so we'll start with sentences for now.
When you say structure of sentences, do you also model the relationship between those elements, like the ordering of sentences?
It's more about contextual information that like some words appear in the same sentence together. Also that there are sentence boundaries. So we can like basically segment the input, and then like we can probably like block out some parts of the input that's not relevant. Yes?
So the idea of taking advantage of structure is intuitively appealing, but why specifically in the context of regularizers?
So we want it to be a little bit more general. Like, so we can model it as latent variables, for example, right? Like each sentence has its own latent variable, and it could be like on or off or something like that. But so that would require changing model class, and it would require changing to non-convex model. Whereas like with our regularization function, if the loss function is convex, our training method is also still convex. So we have that nice property that like learning is easier. You don't need to do initialization and things like that. So I think that's what's like mostly appealing with regularization function. It's a little bit more general, and if the loss function is convex, it's still convex because like the kind of regularizers that we're using is a class of convex regularizers. Okay. Also, I'll show you a little bit about our learning method that was needed because this regularization function basically requires us to use like a new optimization method. Okay, so this is the framework that we're going to work in this part of the talk. So we're going to use regularized empirical risk minimization, where the goal of learning is like to minimize this objective function. So we have a loss function and we have a regularization function, right? And we know that the role of the loss function is to fit the data better, and usually people use regularizer just to prevent overfitting. But I'm going to show you here how we can use it to encode linguistic knowledge as well. Okay, and our focus is going to be on the regularizer, and this is why we call this a little bit like model-agnostic, because the loss function can be like log loss, can be squared loss if you want to do regression. It could be hinge loss, it could be X loss. At least like in theory, it does not matter. Okay. So specifically, we're going to use what is called the group lasso. Okay. Formally, this is what it looks like. The penalty function or the regularization function is just a sum over group 1 to G, and we penalize by the autonormal features appearing in the group. I will have like more specific examples later, but for now, I would like us to focus on like the grouping structure. So when we want to use group lasso, basically the grouping structure has to be predefined. Okay, so we need to define like how we group these features. And where does this grouping come from? It usually comes from domain knowledge. And people have shown if this prior knowledge is correct, it could lead to statistical improvements. Okay.
Sorry, before you go on, can you give a little bit more intuition about this particular regularizer?
So let's say like in the simplest case, let's say we have a bag of words, and let's say we group by the first letter of the words. It's dumb, but like we can do that, right? So this regularization function will choose a subset of these groups. So maybe like after we do learning, only like words starting with letter A will be selected, and others will be selected will be 0. So this is like, so if I have like a marker, I can draw like what it looks like in the.
So you're saying that it chooses a single group, or it tends to prefer some groups?
Yeah, it tends to prefer some. So like if we write down like the optimization problem, we can write it as like minimize an objective function subject to a constraint, right? And so in the three-dimensional case, so the constraint will look something like this, basically. So let's say this is like, we have 3 groups, okay? We have 3 features, W1, W2, and W3. And let's say W1 and W2 is a group, so we'll penalize like that. Oh, my handwriting is terrible. And then, so when we look at this, like, so this is like our objective that we want to minimize, whatever. And so when we look at it from the perspective of W1 and W2, like the optimal will be like somewhere there, right? This is W1 and W2. So that means that this group is selected, but when we look at from the perspective of like W3 and W1 and W2, it would be something more like this, so that it will only choose like a subset of the groups, in this case only W3. I mean, maybe that's not super intuitive, but that's how I find it like intuitive. So basically the basic idea is we only choose a subset of the groups. And we group the features, and then after we do learning, we'll choose a subset of the groups, because like the norm that we're projecting to looks like this in the like in this kind of space, and then this is the objective that we're trying to minimize, right? And the minimizer would be like the part of this that intersects with our constraint. Okay, I hope that's clear. I would be happy to talk more about it like when we meet later. Okay, but so our basic idea is simple. We'll just use we'll just define one group per sentence. Okay. And again, the intuition is that not all sentences are relevant to the prediction. So we want to drive the weights of these sentences to 0, right? And also we've added contextual information. So we penalize words appearing in a single sentence together, basically. And this is what we call token-based group regularization, because if we look at a corpus and we define our grouping structures, and we look at a different corpus, we will have a different grouping structures, right? Because we look at word tokens. Whereas usually this is not the case when group lasso is used in NLP. People groups by feature type. So maybe like all nouns is a group, all verbs is a group. Yes.
So if I understand this correctly, and probably I don't, I think L1 is the regularizer that tends to minimize the number of features, right?
Yes, yes.
So is this basically a generalization of L1?
Exactly.
For the case
it's group L1.
Groups?
Yes, exactly.
Okay,
yeah, it's group L1. It's group plus. Yeah, it's group. It's
okay. And you're using a group because a sentence you're thinking of as a group of words.
Yes, it's exactly like L1, but it operates on groups. So it would turn off like a group, or it would turn on like a group instead of like a single feature, basically. Yeah. Yes.
Since Ryan mentioned, so you're not using L1, you're using L2, although you do want many of the weights to be 0.
So for now, let's just assume that we only use this group lasso. Actually, in practice, we'll add an additional L1, which I will talk about later. So I have like a clear example. Hopefully, this will make it clearer. Let's say that I have 2 sentences in my training corpus. Okay, I live in Seattle. Seattle is great. I think it's great, right? Compared to Pittsburgh. but let's say that we're using like unigram representations, for example. So each word is a feature, right? In this case, we have 6 unique words, so we have 6 features. And then we have 2 sentences, so we will have two groups. Okay, the first sentence is like the red group over here, and the second sentence is the blue group. Okay, and then so what does the penalty look like? This is what the penalty exactly looks like. So that's the L2 norm of all features belonging in a group. And note that so if every group only has its own feature, that just becomes regular lasso right here. So there should be an absolute value over there, but I remove it. Right? If each group is just a single feature, that this just reduces exactly to lasso, right? L1 penalty, right? There should be like absolute value over here. So that would be like WI squared, square root of that. So that would be like absolute value of WI. Yes?
So some documents have like more sentences, so you basically have more groups for it.
Yes, yes. So yeah.
So do you consider the length of the document as well?
Not when grouping the sentences. So basically, this is like the penalty that we use. We're going to like for every sentence, we're going to have this penalty. And so after we do learning, the optimization method will choose only a subset of the group. Let's say in this case, it will turn off the first group, and it will like, which means that all the feature weights for features in the first group will be set to 0. And then it will have some weights for features in the second group. Okay, so maybe this express positive sentiment towards Seattle, something like that, right? And this is like, basically this is like what happens after we do learning. But the problem is in a typical corpus, we will have millions and millions of sentences, right? So our feature space, like the grouping in the feature space, will be like so complex. It will be like there will be millions of groups, and they overlap heavily because words appear in more than one sentence, right? But this is the kind of like effect that we want to get. So we want to like the model to ignore the first sentence, basically in this case, and only uses the second sentence when learning, because we can say that the first sentence probably introduces more noise than signal when learning the weights. Okay. So this just now becomes an optimization problem, right? So this is the kind of regularization function that we want to use. And the optimization that we have now is, yes?
I'm sorry, can you just go back to this slide? So you're saying that the mechanism is going to cause you to ignore words that are shared across sentences? So I see how it causes. Okay, so first of all, it turns off the sentence "I live in Seattle" or downweights it, and in addition, it causes you to downweight the shared words across the sentences.
Yes, yes.
Okay.
And obviously, like this is just like 2 sentences, so it looks simple, but in practice, it's a little bit more complex than that, right? And it could just be that we will retain both sentences in this case. Both are not set to 0 if that's what the model thinks to be optimal.
So I guess, for example, the word "is" probably occurs in lots of sentences.
Yeah, yeah.
And so probably
so it will get downweighted.
Right.
Yes.
So you're saying you're gonna pick out the word "great."
Basically, yeah. But yeah, this is like a very simple example, right? I think the more like insight is that like it's not looking at individual feature or individual word, but when we remove like a particular like set of words, we do it based on like the sentences that appear in our corpus. Because like if we just want to downweight the word "is," we could just use like a standard like unstructured regularizer like lasso, right? It's more about like getting this contextual information in the sentences. Okay, so now we have any other questions? An optimization problem, right? So this is the loss function. It could be log loss if we want to be concrete, but it could be any kind of loss function. We have the sentence regularizer, which is just group lasso, 1 group per sentence. And we also added like a classic, just like L1 penalty on all features for stronger sparsity. This is actually so that we get sparser models. And the problem is existing methods to solve group lasso problems fail to do it efficiently when the structure that we have is millions of groups and they overlap heavily. Okay, so if it's a lot of groups and they don't overlap, it's easy to solve. It's not easy, but there is an efficient optimization method for that. If it overlaps, but only a small number of groups, that's also fine. But when we have a lot of overlapping groups, it's not easy. Yes.
So the second term was what you described previously.
Yes, exactly.
So it has an L1 on the groups.
It has an L2 of.
Sorry, it has an L2 on the groups. And the third term has an L1 on the groups.
No, L1 on each feature. L1 on each feature. Yeah, it's just a standard L1 penalty, the third term, and we just add that because we want stronger sparsity at the end. So like removing the word "it" is basically in the previous example.
So how would you contrast? And again, we're asking lots of questions without.
No, that's totally fine.
Feel free to defer. How would you contrast putting an L2 on the groups and putting an L1 on the groups?
So what do you mean, like putting an L2 on the group? So I don't quite get.
I mean that earlier I misunderstood, and I was saying it looks like you have an L1 over an L1 regularizer, but instead of applying it to individual features, you're applying it to group features.
So that's the effect we get, exactly like that. The form is an L2 norm. It's like confusing. It's not squared L2, it's L2. So this is like L2. So because like, I will write it. So if we only have a single feature, this will be like Wi squared, right? L2 norm of this entire feature, which is exactly like the L1 of this, right? So this is like the generalization of this for like a bunch of like groups, basically, something like that. Because like if every group is just a single feature, then it reduces to L1. So, and there is also squared L2, which is confusing, right? Which is actually what we usually call L2, right? So that's like a different story, but that does not give us any kind of sparsity.
So if I understand you correctly, you're saying that the effect of the particular mathematical formula you're using is to generalize L1 to the groups.
Yeah, exactly.
To achieve,
yeah. So that's why it's called group lasso. I mean, that's not like my thing, right? Just to be clear here, that's not my thing.
Okay.
I'm using, exactly. Yeah, that's the effect we get. The mathematical like notation is a little bit different, but that's the effect, and that's the way to think of it, I think. It's not like we're having like a bunch of like absolute values in terms, and then putting a bunch of like features inside. Okay. Okay, so how are we going to solve this efficiently? So we propose a new method, actually a new optimization method to solve this problem. It's based on the alternating direction method of multipliers. So IDMM itself, it's not new. It's been around since the 60s. It's a very old optimization method. We're going to use it to solve overlapping group lasso problems. Okay, so how are we going to do that? First, we're going to change this into a constraint optimization problem. Okay, now we have a new constraint, v equals mw, and we've replaced the second term by v, and we minimize with respect to w and v. So what does this constraint look like? Let's say that originally we have two sentences. Okay, red, blue, and green, and then red and green. So we have three unique colors. The original feature vector, which is w, has three features, right? Red, blue, and green. So that's the one on the right. Now v is just basically for every sentence, we make a copy of the features appearing in that sentence. So in the first sentence, we have red, blue, and green. We make a copy of red, blue, and green. So these are like the top three boxes here. And in the second sentence, we have red and green. So this is the second copy over here. Okay. And M is just a binary matrix that tells us that the first element of V is a copy of red. Basically, it's 1, and the rest is 0. It's a copy of red. The last element of V is a copy of the green feature. So this is what the constraint looks like, basically. This is the thing that we're interested in optimizing. We have a bunch of copies for that in V, basically. So V in practice is a very long factor. And M is just like mapping. This element of V is which original feature. Okay, so that's what the constraint looks like. And after we have this, with ADMM, we're going to just use augmented Lagrangian technique. Something like that. So we will move the constraint into the objective function, and now we have an unconstrained optimization problem. Okay, so those would be like the fourth and fifth terms over here. So this comes from the constraint, right? We penalize the objective by violating the constraints by like, so we also introduce a dual variable u. So this is like the Lagrange multiplier. We've also added a quadratic penalty over there to speed up convergence, and we have a hyperparameter rho. Okay, so this is it basically. This is like a new objective function that we want to optimize now. Okay, which comes from those like the derivations. Now, how are we going to do that? It's very simple. So at each iteration, we'll just minimize with respect to one particular like vector. So we minimize with respect to w, fixing others. And then in the second step, we minimize with respect to v, fixing others, and then we'll update u. So I have like a little bit more details in this slide. Okay, so in the first ADMM step, we just minimize the objective with respect to w. So these are only the terms that depend on w. I only write down terms that depend on w here. Remove other terms. So this is like from the previous objective. And then when we work out the derivation for this, what we will get is an elastic net-like minimization problem. So if you don't know elastic net, that's fine. It's just a combination of L1 and squared L2 penalty, so like lasso and ridge. And we know that there are a lot of efficient optimization methods out there to solve this problem, like Vista or regularized dual averaging. So this is in the first step. That's what we will do. In the second step, we're going to minimize with respect to v, fixing others. Okay, so these are the terms that depend on v. And when we work out the derivation for this, what we will get is what sometimes is called the block thresholding operation. So basically, v is a long vector, right? And each subvector of v corresponds to a sentence, right? Now, we're going to check the L2 of this subvector, and if it's below a threshold, we set them to 0, the subvector to 0, otherwise we shrink. That's it, basically. It's like very simple, and this step is actually the key to solving these overlapping group lasso problems, because in V, there is no overlap anymore, right? V is a copy, so we can do this in parallel, even though we have like a million group originally, so we can distribute it across a bunch of machines and operate on different subvectors of V independently. So basically, this is the key step. And in the last step, we'll just update the dual variable to like make sure that the constraint is satisfied the next iteration. Okay, so this is it. We have some convergence proof and derivations in the paper, but if you're interested in this, feel free to ask me later as well. Okay, I would also like to mention that there was another work that considered ADMM for overlapping group lasso. And their technique is a little bit different than ours, so they still require some heuristic post-processing step to get exact zeros in the feature weights, whereas this is not the case in our ADMM. Okay, so that's how we're going to solve our optimization problem. Now let's move on to some experiment results. Okay, we did a lot of experiments in the interest of time. Today I'm just going to show you like the first one, topic classification. We compare with 3 different baselines. So squared L2 like regularization, L1 and elastic net. So these are standard regularization functions that people usually use in NLP. They don't incorporate any kind of linguistic structures in the regularization. So this is just like standard unstructured regularizers. Okay, so these are the results. So we have like a lot more results. I think we have like results for 10 data sets. I'm only showing you 3 here. The numbers are classification accuracy, higher is better. Each row is a different data set. So science would mean like classifying documents from 2 related categories in science, like physics and biology, for example. Sports would be baseball and hockey, something like that. And we can see that our method performed quite well. There's more results in the paper, by the way. Also, since our method gives us exact zeros, we can look at the model size, right? We can look at what's the percentage of features that is retained by the model after training. So this is the model size. The numbers are a percentage of non-zero features. And we can see that lasso actually gives us the sparsest model, but it almost always performs worse. So this indicates that it throws away features that are actually useful for the prediction task, right? Whereas our method, it's the second sparsest after lasso, and it almost always performs like the best or the second best on like 10 data sets that we try this on. Okay, so I would also like to talk a little bit about this. So we can like do some analysis. We will check like the V vector and check which sentences were set to 0 by the model and which sentences were retained, right? So this would like tell us like which sentences are actually relevant to the prediction during training and which sentences are not. So that's what we're going to do. This is from an article about predicting whether it's a Macintosh or IBM article. I only show you the top 6 sentences. The article is actually a little bit longer. So we can see that the model, it did something reasonable. For example, like the sender email address does not tell us anything about Macintosh or IBM, right? It's set to 0 in the v-vector. And then like the fifth and 6th sentences, so they also don't tell us much about the label of this sentence. Whereas like the other 3 sentences in blue, they tell us that this is a Macintosh article. So this is just like checking if it actually does something reasonable during training, nothing else. Like it's just like, and then we found out that the model did something quite reasonable, so we're quite happy with that. And this is a randomly chosen article. I did not cherry pick this example. I just choose one. Yes?
So when you're talking about the model size and in this example, you're talking at the level of sentences, but you're not discriminating about words within the sentences?
No. So when I talk about this is actually the model size in terms of the number of features that are retained, so not in terms of sentences. In this case, yes, it is in the number of sentences, but in the previous slide, it's about like, originally we have 10,000 words, so there are 10,000 features. After training, how many features were retained by the model. So in this case, this is...
So what is the meaning of the green column? Is it, you're saying that it highlighted 12 words? I'm confused by the word sentence.
Oh, sentence is, sorry, that's just like our method, basically. That's our method. Our method.
Oh, this is
sorry. Yeah, that's our method, basically. Oh, okay. Bad naming. Okay, I'll change it. But yeah, that's just our method. Okay, the last column is our method, and these are the baselines. Okay, it's not about like how many sentences were selected. Good. Sorry about the confusion. Yes?
These are percentages?
Yes, yes, the percentage of non-zero parameters. Exactly.
So I was wondering back again to your model-agnostic part of the improvement. So this is showing that a particular task using sentence as the structure improve results for
logistic regression. Sorry, I did not mention that. Logistic regression, yeah.
And you get improvements across other tests?
So we did not really try a bunch. I think we tried like squared loss for regression. Similar, we did not try like SVM or like boosting or things like that. Well, in theory, they can be plugged. We did not run experiments for that. Okay, so I just want to mention, like earlier I said that we can incorporate other like more complex structures in the same way through a regularization function. So we actually did that. We incorporate information from syntactic trees, all the topics and brown clusters in the same way, basically. So paper is at ACL last year. We've also applied the same idea to other NLP problems, like learning word representation. So in this case, we incorporate knowledge about word meanings. So we thought that word meanings have to be organized in hierarchy. So we try to impose that kind of constraint when learning word representations. So the paper is still under review. There is a draft at NIPS workshop last year. Okay, so just to summarize what we've talked about so far, I've shown you how we can incorporate a linguistic bias through a regularization function, and I've shown you like an optimization method to solve the resulting problem. Okay, so any questions about this part so far? Because before we move on to the second part, yes.
I guess I'm wondering, the model agnostic part is nice because you can run the same, use the same classifier at test time. I'm wondering if you're losing something though, because it's not doing that sentence selection thing at test time, right?
That is true. That is exactly true.
So
yeah.
I'm curious if you compared it to a latent variable.
So we did. Actually, we did. Yeah, we did. I have the result in the paper. Actually, I think we did. So there were like 2 data sets. So we compared with latent variable SVMs. So this requires initialization and things like that, but it does infer like latent variables at test time. So I think they reported results on 2 data sets. And we compared on these 2 data sets. On one, we're winning. On the other, we're losing. So can't really say much about that. But I think the nice thing about our method is it's convex, right? Whereas like they still need like some clever initialization techniques to get that. But it is true that it does not produce like a summary, right? In our case, during test time, right? It does not infer like the usefulness of each sentence. Yeah. Great question. Yes.
I want to make sure I'm not missing anything. So when you say encoding linguistic knowledge or encoding linguistic bias, how would you state the knowledge that's being encoded?
How would I state? I don't quite.
So I think I understand more or less the mechanism that you're using, but I wanted to step back and think, well, so what is the knowledge being encoded? It's not domain knowledge about baseball. Is it knowledge about which words are more prominent? It's not syntactic knowledge about prepositional phrase attachment. So what's the knowledge here, really?
So in the case of sentences, it's a very simple knowledge. It's just that there are sentence boundaries. But so in this other work that we did, so let's say like we encode like LDA topics. So that would mean like something like word meanings. Or we encode like knowledge from syntactic trees. So instead of turning on and off sentences, we turn on and off like clauses or noun phrases and things like that. So that's probably like closer to what you're talking about, right? Yeah. Like we can turn on like maybe like the other part of the sentence is irrelevant or something like that. So we also tried that in a similar way. So that would be like a parse-free regularizer.
And when you encoded this more sophisticated knowledge, did it result in
performance? In general, like what I observe is that if it's sentence level classification, this is the best one, like encoding like syntactic trees knowledge. But when it's like document level classification, it's not as good. But it kind of makes sense, right? Like if you're really interested in classifying a sentence, you really want to like remove like phrases or parts of the sentence that are irrelevant, right? Whereas like when we have like this giant document, there's just too many groups basically. So maybe it just has too much noise, something like. But in sentence level classification, yes, we observed that one is the best.
I wasn't sure if I understood your.
So let's say we like given a sentence.
No, go ahead.
No, you can go ahead.
Yeah, it's probably better if I ask the question more clearly. So you have a way of taking linguistic information and mapping it into the optimization framework. And these are richer linguistic information. So the question I was trying to ask is, okay, is this richer linguistic information translate to better results on the task you described? So I think the simple answer would be yes or no.
Not always.
Okay.
Not always. That would be. Although like we observe like some tendencies, like some knowledge is more important for a particular task, like sentence level classification. Like there are like some knowledge that's useful for that, but the same knowledge when we apply it to other tasks, it's not as useful. So I would say not
fair
always.
to say that overall the contribution here is more theoretical. It's not like you found an approach that results in a substantial boost in performance other than what you showed earlier. When you say sometimes yes and sometimes no, but you're not showing me a case where you said, look, here's a case where it really had, I took sophisticated knowledge, I injected it into using this framework, and it kicked the pants off of the standard approach. You're just
so I can show you like some example from our ACL paper on that. So that's exactly doing that actually. Although I'm trying to be like a little bit more careful in like the claims I make. So I'm not saying that this is it. Like I found like a way to incorporate linguistic knowledge and this is it. And every time you use it, you'll get improvements. No, so no, I'm like,
sure,
I'm not claiming that.
You're very modest, but in the best case, okay, so not claiming always. What happens in the best case?
Yes.
Which of these regularizers?
The thing is we have like a lot of data sets. We have 10 data sets and they are different. Like some of them are like sentence level classification. Some of them sentiment analysis. Some of them just like topic classification. So it really depends on the task, I would say. But for every task, we found the best results. If we know exactly which linguistic knowledge to encode. But we did not know beforehand. We only found out after we ran the experiment. So it's not like I can say like, okay, I did this beforehand and I found the best results. So that's why. Yes?
So if I wanted to do sentence level classification, you tell me that go use Sparsity regularization. That's what you have done, and it will probably improve my results.
Yes, yes. I would think so.
Roughly?
Oh, I can like show you the numbers if I could pull up the paper,
okay,
but I don't. I can't claim 10% improvement or something like that. Yeah, and it's probably like task dependent and like corpus dependent too. Okay. Okay. So let's like. I think this is like more interesting. Talk, like the second part of the talk, it's about optimizing text representation. It's also more general than what I've talked earlier. So this is applicable to more like model classes. Okay, let's step back a little bit and think about like what we do when we're doing like machine learning on text, right? We usually have a given text, and we usually need to represent it as a feature vector for our input. And maybe we represent it as bag of words, like mostly, right? Or bag of features, right? In other cases. Now, we can ask questions like, so I'm only showing unigrams here, right? But what about bigrams and trigrams? Okay, what about Gaussian grams? Or maybe we can plug like LDA topics there, right? Should they also be included? There's also another set of questions that we can ask. So here I'm showing you count frequency, but is that the best representation? Should we like normalize by the length of the text? Should we take the log? Should we use IDF and things like that, right? Now, what we usually do in practice is we probably spend 4 or 5 hours, try a few different combinations, and then we find one that's quite good, and then we stick with it. And then we build our fancy models on top of that, right? So that's what we usually do in practice. Now, this is not ideal, but probably okay if we only have one data set. But what if we want to do well on a lot of data sets, right? So that means we would have to spend like hundreds or thousands of hours if we're interested in doing well on like 500 data sets, something like that, right? So our idea is that like any other task where it's a little bit tedious and hard for human, we can ask if a machine learning model can actually do it better. So that's what we're going to do. We're going to ask like a machine learning model to find the best text representation for our task at hand. And this is what we call a black box NLP system, which basically takes the raw text as input, and then the system would take care of like feature extractions and then like choosing the classification model and just return the best model. So that's the overall idea of like black box NLP. Okay, and obviously, if we have a lot of tasks, like a lot of data sets, we can also probably generalize across data sets so that we can optimize this faster. So I will also talk a little bit about that later. Now, in this talk, I'm going to focus on the task of supervised learning, but the same idea can be applied to unsupervised learning as well. In fact, we're doing that right now. I don't have the results yet. And I'm going to show you like ideas for text classification, but this is really general. It can be applied for other NLP problems as well. Okay. So what usually happens is we have a training data, and then after several like trial and error, we choose a mapping function. Let's say we choose G2. Okay. In this case, we create our feature vector. Okay. And then we choose our classification model. We learn a set of parameters associated with our feature vector. It could be like 1 weight per feature, or probably more than that. Like in the simplest case, it's just 1 weight per feature. And then usually we have a development set, right? And then we use the same mapping function, create feature vector for our development set. And then using the parameter vector trained on our training data and our def data, we will compute f of x. So f of x is a number. It's like accuracy on def data, or F1 score on def data. It's a single number, or log likelihood on def data. It's a performance metric that tells us how good we are, and we hope that serves as a proxy for our performance on unseen test data sets, right? So that's what we're all interested in. Now again, like if we improve the model, we're focusing on this part of the pipeline, right? It does not just mean like if we change the model, it's not just like learn. But our focus in this part is going to be like a little bit further behind the pipeline. So we're going to focus on like what is the best way to represent this tag as an input to our machine learning model. Okay. But of course, at the end of the day, what we care about is we want to optimize f of x, right? Because we want to do well on unseen test data sets. And x here is basically a function of everything. It's a function of our training data. It's a function of our def data. It's a function of our G function. It's a function of the classification model we choose, the parameter associated with the classifier, and things like that. But to simplify, let's just call it f of x for now. Okay. Is the framework clear? Okay. And now, when we want to optimize text representations, what are the axes that we're going to be optimizing over. So there are like many choices. These are like the choices that we use in our experiments. Okay. First one is we're going to optimize whether what is the best n-grams that we want to use in our case. So maybe in your case, if you don't use like bag of words, it could be like the set of features or character n-grams and things like that, right? We're also going to optimize over the weighting scheme. Okay, so which one is the best weighting scheme for this particular task? Okay, and then we're also going to optimize over whether we should remove stopwords or not, because these can be different, right, for different data sets. Now, this set of choices represent like our G functions, basically, right? These are like the choices that directly like create our G functions. But these choices also interact with other choices that we make during learning. For example, if we use more n-grams, maybe we need stronger regularization, right? Because we have more features. We probably need to train longer, right? So we're also going to include like these decisions that interact with our representations. So we're going to decide what's the best regularization function to use for this particular data set. We're also going to choose what's the best regularization strength. So this would be like choosing a number from an interval of real number, right? So what is the best regularization strength for this data set? And we're also going to use like convergence tolerance, which we hope serves as a proxy for like how long we should train the model. So this is also like choosing a number from interval. Now notice that we only have like 6 things that we're optimizing over, but the number of possible combinations, well, in this case it's actually infinite because we have real numbers, but let's say we discretize that into like 5 choices, right? But the number of possible combinations is already easily in the thousands, even if we discretize this into like 5 and 5, something like that. Now, it's obviously impractical to like try all these possible combinations, right? Because there's too many of them. So we need to be like a little bit more clever in choosing which one to try, right? So that's what we're going to do. In our experiments, we're just going to try 30 combinations. That's 30 out of like this possible 1,000 of combinations. Okay. Now, there are also other things that we can include here in the same framework that we did not do in our experiments, but can be easily incorporated in the same way. For example, what is the best classifier for this particular task or data set? Should we include like word factors, or should we stem, or things like that, right? They can be easily included. We did not include them in our experiments. So how are we going to do that? We're going to use Bayesian optimization for that. So how many of you are familiar with Bayesian optimization? Okay, so there's a few of you. I can go through this a little bit like quickly, I guess. So it's a framework for optimizing an expressive function. It's very popular in computer vision. It has received very little attention in NLP. In fact, I've never seen any based-up paper in NLP, which is like very surprising because I think this is very useful. Okay, so the model consists of like 2 important components. The first thing we need to have is a probabilistic model of f. So this will give us probability of f of x. Again, f of x is just a single number, like accuracy, at a given x. So this is usually called the surrogate model. Okay. And the second component is what is usually called the acquisition function. It's a function of x, parameterized by the probabilistic model p. Okay. So what does this do? A good acquisition function ideally should return high values at axis, where the probability of fx is predicted to be high by the surrogate model, or the surrogate model is really uncertain about what f of x is at a given x. So this is the classic exploration trade-off based on the surrogate model. Okay, so I hope that's clear. Based-up model is actually very simple. It consists of 3 main steps. The first step is basically, given the current probabilistic model p of t, we maximize the acquisition function. Okay, and let's say for now assume that this can be done easily. Okay, and then we get x of t. Okay, in the second step, we're going to compute f of xt. This is the step that's expensive for us. This requires extracting features from training data, learning the model, extracting features from depth, computing accuracy. So this step could easily take like several hours for large-scale problems, right? Computing f of xt, right? Because like at a different xt, we need to like retrain the model basically. And then in the third step, we're just going to simply update our surrogate model p, and then we iterate, and then we move on to the first step again. So this is basically Bayesian optimization in a nutshell. It's very simple, and I haven't talked about the surrogate model or the equation function at all, but the most common model for the surrogate model is a Gaussian process prior. So we assume that f of x is drawn based on a Gaussian process. It's parameterized by a mean function and a covariance function. And the nice thing about using a GP prior is that the posterior, when we update the surrogate model, is still a GP. So I'm not going to talk about GP in detail, but that's the basic idea that we need to know for this talk. And for the equation function, the most commonly used is basically expected improvement. And the only thing that we need to know for the purpose of this talk is that if we use a GP model, it has a closed form solution. It would be a function of the predictive mean and the predictive variance as given by the GP model, so it naturally balances like exploration and exploitation. Okay, so this is just like some background about Bayesian optimization. Okay, so that's what we're going to use to optimize our text representations. Now, we did 8 experiments on benchmark classification datasets. The first thing I would like to say is that the best representation found by our model is different for a different data set. So I'm showing 5 data sets here. So for example, like the choice of n-grams, in some cases, we need to use unigrams, bigrams, and trigrams. In some cases, bigrams alone is enough, which is quite surprising. Right? The weighting scheme is different. Whether we should remove stop words or not is different. And the best regularization is also different. So I guess I just want to say, like, I work on NLP quite a bit, I guess. I probably wouldn't be able to come up with these exact combinations like in less than a week, maybe. So I guess like it's nice to have like a model like where we can press enter and do this like in several hours and find the best like representation for us. Right? Now, what about the results, right? So here's the first set of results. This is from a movie review data set from IMDB. And our model is highlighted in purple. It's just a logistic regression, but we optimize the representation. Okay, first, I'm going to compare with linear model baselines. They are mostly SVMs. They should be comparable, right, to logistic regression, SVM, but we can see that our model actually performs like a lot better in this case. So the numbers are sorted. So this just shows that even for NLP experts, it's not always obvious what the best representation is. And I think they use log frequency, they use some normalization, and it turns out that that's not optimal, right? And if we optimize this, we can easily get better numbers without even like putting a lot of effort. So I think this is quite nice. Yes?
And do you know the upper bound, like by checking like all possibilities?
No, I did not. There's too many, so I don't know like what's the optimal like numbers. Then we can also compare with even more complex models. Okay, so models in green are actually nonlinear models. They are variants of neural networks, and surprisingly, we're doing like quite good. So we're better than restricted Boltzmann machine. We're comparable than a feed-forward neural network here. Right? And we're slightly below like sequential convolutional neural network, but I think this is fine because we're just taking the simplest model. We can also optimize like what's the best classification model for this particular task, or we can even like take neural network and optimize the representation for like feed-forward neural network, right? For example, like it takes like trigrams in this case. So I think this is pretty nice. So we also did experiments. So this is the second set of results from a different data set. The data set is to predict whether a congressman will vote yes or no. The baselines in this case are mostly variants of latent variable SVMs. And our method is like outperform all of them using a simple logistic regression model. Okay. Yes?
So the sequential model-based optimization paper that you cited from Hutter and also, they also have an implementation in AutoWeka that does this kind of hyperparameter optimization. So this is an application of that, or is that an extension to feature selection or feature design?
So yeah, it is hyperparameter optimization, but we're like focusing like not in terms of hyperparameters during learning, but about like how best to represent the text as an input. So if you can think about, yes, you can think about it as hyperparameterization, but but for me, it's a little bit like behind in the pipeline, right? Like it's
much for feature design part, right?
Yes, exactly. Also, okay, so this is the last set of results I'm going to show. We have more results in the paper. It's basically, so this is sentence level sentiment analysis. It's basically the same story. Our method is better than previously published linear model baselines. it's compatible with recursive neural network and matrix vector recursive neural network, it's still a few points off below the state of the art, but again, I think that's fine because we're just using the simplest model. So I would also like to mention, like, so when we have a lot of data sets, it makes sense to like optimize over like this collection of data sets such that maybe we don't need 30 trials for each data set. Maybe we just need 5 or 10, right? If we borrow information from previous data sets. So that's, I did some work on that. So basically, our idea is that each data set has its own min function, and we transfer information through the covariance function. So this is at AI Stats last year. I'm not going to talk about the paper in detail in this talk, but feel free to ask me later if you're interested in that. OK, so just to summarize, in the second part of the talk, I've talked about how we can optimize text representation by treating it as a global optimization problems. And I've shown that we can get like really good results using a very simple model. It's actually compatible with some of the more sophisticated models, and in some cases, it's even like around the state of the art. OK, I would like to conclude by mentioning some of my ongoing and future work. So I'm currently interested in applying the same technique for unsupervised problems, specifically like document clustering on unsupervised structure prediction, like part of speech induction. Okay, I think this is one of the key components to unlock the true potential of unsupervised learning, because in unsupervised learning, so the representation interacts with like where we initialize, right? Obviously, or what's the best like training method to do this? Like, should we directly take the gradient? Should we do EM and things like that? So I'm excited to see like whether this can help in that case as well. I think this has the potential for significant improvements. The other thing I'm interested in is like to see if this works well for other NLP problems. So if you have your own NLP problem, I would be excited to see if this could at least like squeeze a little bit more points out of your existing model by optimizing the representation. On more of the algorithmic side, I think this is related to like multitask Bayesian optimization, parallel Bayesian optimization, and things like that. So I'm also interested in that as well. And on more of the application side, I think like my goal is basically, my longer term goal is to make NLP be easier to use for everyone. So having black box NLP makes it easier to be useful for like other people who don't work on NLP, but what about like non-computer scientists, basically, right? So I think like having like a natural language interface to this, where we can query in natural language and return like the best model, would really help like people make decisions, people that are not like computer scientists like us. Okay, so that's it. I would like to mention some of my collaborators throughout my PhD. My advisor, if you don't know, Noah Smith on the right. And I've also worked on other NLP problems like temporal models of text and information extraction. So if you're interested in that, feel free to ask me later. Okay, that's it. Thank you so much. I would be happy to take questions.